So for our fourth example, let's find the volume of the solid above the cone, z squared equals x squared plus y squared, and below the sphere, x squared plus y squared plus z squared equals z. I'm noting that the sphere is the same by completing the square to the sphere I've given below, which might give you a better sense of how to draw it, but you might find the first form of it easier to work with, actually. Good luck! Okay, now if you're still with me, let us compute the volume. So, above the cone and below the sphere, this is basically the same region that we gave before the ice cream cone, except I've moved the sphere, the center of the sphere, up, and so it's actually now lines up a little bit better with the cone. So the way I prefer to think about this problem is by first changing my x's and y's already to polar. So let's just go to r and theta, and so my cone looks like z squared equals r squared. So z equals plus r, z equals minus r. So this is the picture where we've got two lines of slope 1. Didn't like how I drew that. Let's try it again. Slope 1 and slope minus 1. And when you spin these around, they give you the cone. But it's easier to think about it in this slice at a given angle theta, because things are going to be rotationally symmetric. Okay, and the sphere in this perspective looks like r squared plus z squared equals z, or r squared plus z minus a half squared equals 1/2 squared. Squared. If these two lines don't look the same to you, you can expand or FOIL out z minus 1/2 squared and combine it with this 1/2 squared, and you'll get the expression given above. If you want to go down from the top line to the bottom line, what you have to do is move the z to the left side and then complete the square so that you realize that z squared minus z is part of z minus a half squared, but then you have to figure out what the constant is to add and subtract. And I'm just saving us that effort. So this, if we're going to draw it in the RZ plane, it looks like a circle. And let's write it. This looks like a circle of radius 1/2 and center at 0, 1/2 equals RZ. So R equals 0, Z equals 1/2. So here's the center of my sphere, and a circle, and its radius 1/2. And so if I go out to the right 1/2, I'm actually at that line of slope 1/2. So these connect up, and so this circle looks kind of like this. And so now imagine spinning this around the axis, and you've got the green thing is a sphere, and the blue crossing lines become a cone. And that's what we're looking at in 3 dimensions that we want to find the volume of. So you could, if you really wanted to, well, it's a surface of revolution, so you could use Calc 2 techniques to try to compute the volume using the disks method, or the shells method. I'm absolutely not going to do that, though. I'm just going to convert it to spherical coordinates. So let's make sense of it, though. So we kind of have we got options. So here's the region that we actually care about. So above the cone and below the sphere. This looks more like an ice cream cone I'd be happy with, right? It looks like pretty well scooped on top. It's got a full hemisphere of ice cream sitting on top of the cone. And if you spin it around, you really do see an ice cream cone. So, This looks like something like this, but a lot wider. It's a pretty wide cone. So let's try converting it to polar coordinates in the ZR plane to give the equation in, or to give an expression in spherical coordinates. It might be useful right now to realize we already kind of have it set up to do cylindrical coordinates. So cylindrical coordinates are Cartesian slices in the ZR plane, so that would be vertically like this. And so cylindrically, the volume is going to be given by a triple integral of dv. For cylindrical coordinates, that's r, dz, dr, d theta. Theta, we already said this is rotationally symmetric. That just goes from 0 to 2 pi. R is going from 0 up to 1/2. And that's my bounds as I move along here. And then z, the hard one, is going from z equals r all the way up to z equals the semicircle up above. And so we're going to want to go up there and actually solve one of these expressions, probably this one here, for z. So if I do that, I get a quarter, so a half squared minus r squared. I'm going to take the square root of that, and then I'm going to add a half equals z, and that will be my upper bound. So up to 1/2 plus the square root of r 1/4 minus r squared. And I'm writing tiny, but it's not that. It's already evident that that's maybe not the best way to go about doing this problem. So let's try instead converting it to spherical coordinates. Let's move down a little. So in spherical coordinates, we want to find bounds. So it's already kind of straightforward that we're going to ignore the left side. So ignore this side, because you'll get there by spinning. So you only ever need to deal with the right half of the ZR plane, as long as it's rotationally symmetric and theta is going all the way around to 2 pi, because it will spin around and the thetas between pi and 2 pi are going to fill up that other half. So it looks to me like I'm starting at phi equals pi over 4, going up here to phi equals 0. And so I say starting, I mean finishing, so it goes in that direction. And at any point in between, you're starting here and you're going out to that circle. And now is the point where we realize, hey, we don't actually have an expression for that circle in spherical coordinates yet. And this is where this first version of the equation is much easier, because r squared plus z squared is rho squared in spherical coordinates. So let's put it in spherical coordinates. So take that, and r squared plus z squared is actually rho squared. And z is just rho cosine of phi. And so this inner expression, this is the sphere in spherical coordinates. It's close to the sphere. In fact, rho, if we move it all to one side, this looks like rho squared minus rho cosine phi equals 0. And so there's two ways the left thing could equal 0, right? You can factor it as rho times rho minus cosine phi. So either rho is just 0, so that's a sphere with no radius, so that's not what we want. Or rho equals cosine of phi, and so that is in fact the expression we want. This is the sphere. And so this might seem kind of out of nowhere, but you should think about this as similar to circles and how they show up in polar coordinates as like r equals sine theta and r equals cosine theta or 2 cosine theta are these kind of offset circles that are tangent to the origin, but have centers on either the z or r or x or y axes. Okay, so I've zoomed this out a little bit so we have more space to write, but now the volume should be a triple integral. Let me leave myself plenty of space. My volume form is rho squared sine phi d rho d phi d theta. We already said theta goes from 0 to 2 pi. Phi is going from 0 up to pi over 4. And then rho, we now know, is starting at 0 and going out to that graph. So starting at 0 because it's starting at the origin, it goes out to the circle, and the circle is cosine phi. And that is how you'd find the volume of this ice cream cone. If you want to go solve this integral, which is the first one that we have seen with a function actually up in one of the bounds, it will not be hard. After you do the row one, you're going to get some u sub e things for the d phi section. It's totally fine. You should get this to be pi over 8 for your volume.